All right, everyone, it's time for the ACOM seminar. So today, it's my pleasure to introduce Dr. Colleen Rosales. Dr. Rosales is the Strategic Partnerships Director at OpenAQ, where she builds strategic relationship with air quality stakeholders worldwide, introducing people to the OpenAQ platform, spurring data-informed projects that advance clean air objectives, and supporting partnerships across sectors and geographies. Colleen received her undergraduate degree in chemistry from the Institute of Environmental Science and Meteorology at the University of the Philippines. And prior to her PhD, she worked with the Aerosol Technology Monitoring Lab at the Gwangju Institute of Science and Technology in South Korea and at the Philippine Nuclear Research Institute. She received her PhD in environmental science from Indiana University, and she is currently doing postdoctoral research with the Air Quality Research Center at the University of California in Davis, where she programs high throughput comparative analyses of instrumentation for air quality monitoring. And in her spare time, Colleen fundraises for undergraduate school in the Philippines and promotes climate policy with her local Citizens Climate Lobby chapter in Indiana. Today, Colleen will be talking about open ambient air quality data access through OpenAQ, as well as indoor-outdoor chemical relationships from household cleaning activities. Before I start, I'd like to remind the people following online that you can enter your questions in the space below the video at any time during the talk. And at the end of the presentation, I will read these questions to Colleen. And so with that, Colleen, the floor is yours.
Thanks so much, Kyle. Thank you for that kind introduction. As Kyle mentioned, I'm Colleen Rosales. So today I'm going to speak with you about two things. One is indoor air and how we bring our knowledge of the outdoor air into the indoors to better understand all of the processes indoors. And then I'll move on to how we can access ambient air quality data through OpenAQ. A part of this introduction, Kyle already mentioned, but I thought I'd just also bring up some of the past research that I've done. So I have always been in the mix of indoor and outdoor air pollution. So I started research back in the Philippines. I was doing particulate matter sampling in areas where there's area pollutants and whatnot. And then I moved on to do a PhD at Indiana University with Professor Phil Stevens, where we did instrumentation for OH radicals, first looking at the ambient air and then moving into the indoors and applying our knowledge of radical chemistry into the indoors. And currently I'm doing my postdoc at UC Davis and now looking at particulate matter from CSN or chemical speciation network filters and looking at the elemental composition of those and how we can compare XRF to ICP-MS for those CSN filters. But today, like I mentioned, I'm going to speak with you about, radical chemistry and how we brought these knowledge from the outdoors into the indoors and to better understand the processes in the indoors. And then also connecting that with ambient air quality and how we can access data through OpenAQ. So part of this, you probably all already know that we have primary emissions in the outdoors that are, directly emitted, some examples of which are nitric oxide and volatile organic compounds, either from anthropogenic or biogenic sources. And then we also have radicals that usually in the outdoors is primarily photochemically generated. And so with the reaction of these, we get some secondary pollutants such as ozone and secondary organic aerosols. And that's not as straightforward as it was I showed in that previous slide. It's really more complicated than that. And what I wanted to highlight here is the central role of radicals in this whole process. And so radicals in the outdoors, they're photochemically produced, but also there's other sources of radicals. And the question in our mind is that in the indoors, is this still true? Is it still photochemically produced? We know that in the indoors there's less sunlight, and what are the processes that the radicals initiate in the indoors? So bringing our knowledge of the outdoor chemistry into the indoors, we already know the mechanisms. The question is that, does it still hold true for the indoors? Um, so in the grand scheme of things, the question that we really wanted to answer is that how do everyday human activities change the chemistry indoors? And so bringing our knowledge of the outdoor chemistry into the indoors, and also knowing that there's drastic differences in terms of the amount of sunlight, and then also the spatial scale in the indoors. How does that change the processes in the indoors? So again, you'll see this schematic over and over. But in the indoors, we have our primary VOC emissions. What I'm going to focus on today is cleaning products. And then you have your indoor oxidants. One question we have is like, where do these oxidants come from? Specifically ozone or OH, where does this come from? And then the intermediates, some radicals and oxygenated VOCs, and then how that leads into the formation of secondary organic aerosols. So to answer this question, we collaborated with Purdue, IMT Lil Dewey, our JLE group, and this project was funded by Sloan Foundation. This was done in 2019. And this led to a publication in a really prominent journal. But I think the most important outcome of this is that this research made it into tabloids. So we were able to kind of send this message in terms of what is the level of pollution that one can be exposed to when using cleaning products. And what's really interesting is that I'll say the ending of the story here right away is that you can experience the same amount of air pollution from like the PM, similar to that coming from a car's exhaust. And I think what's the most interesting part is that this is not like in visually, it's not like combustion. You don't see smoke, but when you count the number of particles, and as we will see later on, it's the same amount of exposure as you are like, standing in a street canyon or breathing in car's exhaust. So without even like doing any sort of burning or combustion inside the home. So onto the, how we looked at this process. Again, the same schematic here. So we looked at the primary VOC emissions using PTRMS. We looked at the indoor oxidants using an ozone analyzer for ozone, and then LIF phage or laser-induced fluorescence assay by gas expansion for the OH radicals, and the same instrument for HO2 and RO2. And then for the oxygenated VOCs, we looked at those using PTRMS. And then for the secondary organic aerosols, we watched this grow using a whole suite of aerosol sizers. So we were able to see from the growth from the UFP or the ultrafine particles up to the biggest size range. And so I'm not going to dwell too much on the instrumentation and on that, but I'm very happy to answer questions, especially about the LAF phage. That's what I did my PhD on. But to move on to the results here, I'll show you the first part of the results here is these three panels, the primary VOC emissions and ozone here are both primary. And you can see that so the gray shading is when the mopping was done. So the mopping product or the cleaning product that was used contained monoterpenes. So primarily alpha-pinene, beta-pinene. There's also limonene in there, also camphene. All of these monoterpenes have the molecular formula of C10H16. So all of yeah, it's a combination of all of these monoterpenes. So unfortunately, with like knowing C10H16, we're not able to really drill down on which one of these is the main contributor to this primary VOC emissions. So in any case, you see here primary VOC emissions and ozone, and then you can see the titration of ozone on there. So the ozone that is in here is from the outside making its way to the indoors. That's why you will notice that it's about 5 to 10 ppb when the normal ozone concentration, at least in this location, is 10 to 45 ppb. But what also you can notice here is the concentration or mixing ratio of your VOC emissions that was observed during the mapping period. It got up to about 300 to 400 ppb, whereas your usual outdoor limonene concentration would be in the 0.1 to 2 ppb. So we're almost 2 orders of magnitude over the usual outdoor limonene concentrations. And so for us to be able to track that evolution from the primary to the secondary, we also need to look at the intermediate. So shown here in the bottom are the radicals. So we measured both HO2 and RO2. And then I'd like to note here that your typical outdoor HO2 concentration is about 10 to the 8th to 10 to the 9th. And we see here we're, almost, half 5 times 10 to the 9th in this process here. And you will also see that there's that quick rise and kind of quick burst of all of these radicals during that mapping period. And shown on the right here is just a mechanism for that. So what we see here is that we were able to see the radicals as VOC ozonolysis as a rapid source of well, not yet on the secondary organic aerosols. We're still on the radicals, but at least VOC, what we see here in the first part here is that VOC ozonolysis is a rapid source of radicals in the indoors. So continuing on that story, so we wanted to see the evolution from the primary up until the formation of secondary organic aerosols. And so we looked at the selected volatile oxidation products. So we mapped out what are the possible oxidation products, knowing that our oxidants are, ozone and OH. We mapped out what are the possible secondary and so on volatile oxidation products. And so some of these are listed in here. There's a lot more, but these are the ones that are tied to the monoterpenes that we initially saw. And then so those that's the intermediates. And then this panel E and F shows you the particulate matter that was formed during this process. And so you'll see here the particle number size distribution as well as the particle number concentration. And so what you can note here is that one, the peak particle concentration values, especially this one and the second one, is close to traffic impacted areas. So in the literature, you'll see values that are close to what is shown in here. And so that's where that conclusion of being with that 15 minutes of cleaning is almost the same as being outside and being exposed to car exhaust. So this is I guess I've mentioned this already, that we saw in the indoors that VOC formation, or sorry, VOC reaction with the radicals or with ozone forms your radicals and your intermediates, and then leads to the SOA growth. And what's really important to highlight here, one, again, this is knowledge that we already know from the outdoors. However, in the outdoors, it happens much slower, and also it happens much slower in the outdoors. So in the indoors, we were able to see it within that span of 15 minutes. And then also this is a non-photolytic way of radical production in the indoors. So we know that in the outdoors, it's mostly radicals are formed due to sunlight, or I mean, with the presence of sunlight. In the indoors, we have another way to produce radicals. And then here, we just wanted to extend that study into, exposure and how much of that is deposited into the human body. And so what we show here is that the deposition in different sections. So head, airways, tracheobronchial, and the pulmonary. And we compared those two mapping periods to a background, urban background, and street canyon. And the main takeaway here is that this indoor smog event that we see during mopping, or this air pollution event that we see during terpene mopping is equivalent to about 1 to 4 times that of outdoors. And so that's why we termed it, or well, we labeled this event as an indoor smog event. Again, that's something that us as scientists that look at SOA production and VOC reactions, maybe that's something that's not very surprising to us, since this chemistry has been known in the outdoors, and this chemistry has been established. But at the same time, being able to connect that to our everyday activities, I think, was the biggest impact of this study. And so here, these are just the conclusions, and again, we also wanted to connect this to more practical actions, as well as what can we do with all of these conclusions, right? And so at the bottom here, we did modeling as well, in terms of trying to understand what parameters can we change to decrease this exposure to these particles from mopping and from these cleaning products. So we looked at, changing the ozone, as well as changing the air exchange rate. So what we found was that indoor ozone must be kept below 1 ppb, as well as air exchange rate must be increased to about 5-fold to avoid reaching elevated particle mass concentrations at that very short period of time. So that was the first part of that, cleaning products, and how we are exposed to particulate matter from cleaning products, and all of these secondary formations. The next part of this is that we also have other sorts of cleaning products at home, one of which is bleach, for example. And so bleach is also a very good source of radicals, not just OH radicals, but chlorine radicals as well. And so we were also curious, how does this change in the indoors, and how does this affect the processes in the indoors? How are these radicals formed in the indoors? So we know that photolysis is a way to produce OH and chlorine radicals, and we're curious if this is still going to happen in the indoors. So this part of the experiment we did during home chem. Some of you may know home chem. This was done in 2018 with 20 plus research groups from 13 different universities. We were at UT Austin for a month in a 1,200 square foot manufactured home, where we did experiments on cooking, cleaning, occupancy, and all sorts of indoor experiments at this test house. So this is just how it looked at the inside of the house. It looks like a normal house, except there's particle counters inside. We also have our other instruments outside in trailers. But like I mentioned, we did cleaning and cooking and occupancy experiments in this house. And in light of the upcoming holidays, we also I'd like to share with you that we made Thanksgiving, had a fake Thanksgiving in July. We, cook turkey and have all sorts of Thanksgiving food in there as well. I'm not gonna talk about much this today, but if you want to read more on that, there's a short link to an independent article as well as my colleague Emily Reedy's paper, where she discusses all of the radical formation during our fixed giving. But I'm gonna move on to a different experiment during home chem, which is a layer day, where we had 3 volunteers occupy the house the whole day and kind of simulate a living situation in the home. So there's cooking, cleaning, and occupancy experiments. And then, so the main conclusion here is that with HO2 and OH radicals, we were able to see this only during the bleach cleaning period here. So these 2 gray shaded areas are cooking periods. We've cooked breakfast and guess this isn't lunch. This is more like dinner-ish, late lunch. But this blue period here is when we did the bleach mopping. And so it's kind of, if you look at this HO2 and OH concentration, it's kind of quiet the whole day, sitting around the noise. But during the bleach mopping period, we saw that increase in the radical concentrations, both for HO2 and OH. So the top part here is the photolysis frequency. We also had a something that measures not JNO2, but a spectrophotometer inside that we can extrapolate what the photolysis frequencies are for JHOCl and Cl2 indoors. So that's how we're able to have this plot up here. And so you can see that during that time, that's when sunlight was up in that specific area. So that's when the HO2 and OH are highest. So there's still photolysis happening in that specific area of the house at that certain time of the day, which happens to be the afternoon. And so just depending on what side the window is facing. And then the last one here, we had Cl2 and HOCl concentrations. And what you will notice, both HOCl and Cl2 concentrations are high during that period. And that, comes from the bleach cleaner that we used. I'm also looking to tease out the data a little bit more and explore the PM data during this time. But yeah, we saw that rise in radical concentration during that day. And so we wanted to, again, this is not new. This is not news. We've seen this in the outdoors, especially in marine areas where SOA is, influenced by the presence of salts. And so chlorine radical and SOA formation in the outdoor coastal areas have been, observed previously. So again, this is, bringing our outdoor knowledge into the indoors. So in the aim to understand that, we also did some more modeling. So we used MCM and then implemented a chlorine radical chemistry. And then with the addition of that, we were able to see that, yes, indeed, all of the OH radicals and HO2 radicals that we saw was due to the initiation of the chlorine from the chlorine radicals. And so what is not like shown here is that much actually of the propagation was from the chlorine from Cl2 rather than HOCl, which I guess intuitively one will think that this is, from HOCl, but it's actually from Cl2 photolysis. So to continue on this chlorine story, in the same field campaign that we did the monoterpene mopping and whatnot, we also did bleach mopping. And then during that time, again, this shaded areas, gray shaded areas are mopping periods. And we looked again at, radicals, and then the particles that may be produced from this. Unfortunately, we didn't have chlorine measurements during this time, but we were able to see the particle concentrations, evolve during this time um, of mapping. And so uh, again, this is not news because we've seen these sorts of chemical reactions in the outdoors. Chlorine chemistry has been known, but in terms of its applications, practical applications to us as indoor as we live indoors, what should we do? What should we act on to protect ourselves from these particulate pollution? So, again, increasing the room ventilation, don't use bleach in direct indoor sunlight, or use a different disinfecting product if you can. And so again, just some more takeaways for our daily lives. VOCs tend to build up inside the house over time. Our houses are reactors for all of these indoor component, or for all of these chemical components. Ozone can make its way from the outdoors to the indoors, and then also contribute to that chemistry in the indoors, as we've seen in the monoterpene mapping experiment. And then also our personal activities can generate indoor oxidants and enhance secondary aerosol production, up to the level of it's almost like you're outdoors being exposed to a tailpipe. And then also, yeah, human activities, ventilation, lighting, time of day, all of these are important to indoor chemistry. And so, and this is sort of my segue into the, accessing outdoor data through OpenAQ. So we know that like I mentioned, ozone and maybe NOx can make its way from the outdoors into the indoors. And so is it possible to maybe schedule your activities or know what the level of ozone is outside? Answer is yes. And so through OpenAQ, one is able to access, air quality data. This is a universal and open access platform for accessing air quality data. And so OpenAQ is an aggregator of air quality data. OpenAQ is also a nonprofit working to fight air inequality by providing universal access to air quality data. Currently, we have 44 plus billion data points in 56,000 locations all over the world. And this is growing each day as we, ingest a lot more data, both from reference monitors as well as air sensors. We focus on criteria pollutants as listed in here. And also some are not criteria pollutants, but more on the air pollution side. We also have some more that are kind of climate change related, but really you'll see that the wealth of the data there is more air pollution related. Since like I mentioned, we are an aggregator, so we aggregate all of these data into a one-stop shop platform. And so all of the publicly available data is you know stored in OpenAQ, and then also we play a role in convincing governments and institutions to open up their data, as well as we're here also to support researchers and other community organizations and everyone that is monitoring the data and wants to put it in a publicly accessible platform. And I'll talk more about that in a little bit here. But we also have, as a user, for example, if you wanted to look at the data in OpenAQ and maybe use it for your modeling purposes, we have a couple of data products listed in here. We have the API, we have the archive, we have the website, which is the OpenAQ Explorer, and our very new command line interface. And so I'll walk you through some of that in a little bit here. So OpenAQ, like I mentioned, we are a nonprofit, and also with wrangling the world's data, the world's air quality data are for people. um, so Chris is our executive director, Russ our director of technology, yours truly, and as a strategic partnerships director, and Gabe as a data analyst and developer. And so, half of the team, Russ and Gabe, they're the ones working to, make sure that all of these data are available at OpenAQ reliably. And so we were founded by Krista, who is an alumni of CU Boulder, and by her husband, Joe Flasher, who is a software engineer. And so together they built OpenAQ. And so a lot of that history you can read also in here. So we started out aggregating reference monitors, and then now with the rise in low-cost sensors, we also have aggregated those. And actually, majority of the data in OpenAQ is from low-cost sensors. So we also produce reports. So one of the reports that we've produced recently, well, about a year ago, is the global landscape, where we looked at the government monitoring of all over the world for air quality. And we found that 61% of the countries do monitor air quality. However, only 53% share air quality data. There's still a sliver of that do not share their data, but monitor air quality. And then the rest, about 39% of the countries have no evidence, or we didn't find any evidence of air quality monitoring. We also have worked with the Latin America Early Career Earth Scientist Network to translate this in Spanish and Portuguese. And so if you're interested in contributing to our 2023 report, I invite you to join us in writing this report and contributing to this report, and finding out which countries do have their air quality monitoring and whatnot. And so we also mentioned here our 4 key criteria for open data, which is, having physical units, station-specific coordinates, timely fine-scale temporal information, and programmatic access. And you can read more about that in this report, which is available here. And if you're interested to know which countries do share their data and don't share their data, the worksheet is down here. So moving on to the use cases and partnerships that we have at OpenAQ. Who can use the data in OpenAQ, or who has used the data in OpenAQ? In the past, it's really very air quality research centric. I mean, the user base. But now we're, really working to move outside of the air quality research space and have OpenAQ be useful also to folks like doing climate research, also to public health entities, community-based organizations, journalists and storytellers, even app developers and tech companies, and basically anyone who cares about air quality. So I'm gonna the next few slides, I'll talk about some of the use cases for OpenAQ, or for the data in OpenAQ. So one is Cleaner Catalyst, which is this huge program funded by the USAID. It's a 5-year program. And the goal is to set up reference monitors in Indore, India, Jakarta, Indonesia, and Nairobi, Kenya. And our role in OpenAQ is to support the data management and data hosting for these pilot cities. And so once those reference monitors are set up, their data will be available in OpenAQ. Next, 2 fun apps that use the data from OpenAQ is Smoky Air Pollution Bot and Shoot I Smoke. So both of these are have the intent to raise awareness about the PM pollution outdoors. So Smoky Air Pollution Bot is a chat bot. You can chat with it via Facebook Messenger and WhatsApp. It will tell you what the levels of pollution are outside, and then also tell you what should you do to avoid, say, for example, if there's hazardous levels of PM outside. And then Shoot I Smoke is an app that tells you the equivalent of the PM pollution outside to the number of cigarettes smoked in a day. So even if you're not smoking, there's that equivalent of level of pollution that you might be breathing just by breathing PM 2.5. So kind of fun apps in terms of awareness and education for the public. And then there's also, machine learning oriented projects and initiatives. So one is AQAI, which is a UNICEF Venture Fund backed organization based out of India. They're using machine learning powered predictive models for monitoring air quality in areas where there's little to no air quality monitoring. One example or two examples of their works here are in Belize and Latin America. And then we also, the data in OpenAQ is also being used in predicting what we breathe, which aims to have a forecasting algorithm for air pollution events in the city of LA. And so this will inform citywide air quality policies in LA. And then also, OpenAQ is not just a data platform. It's also a network and a community of air quality researchers. So one example that I always like to highlight is Collins. Collins is currently a postdoc researcher at the University of Georgia, but he is originally from Ghana, and he's built he's set up a lot of low-cost sensors, not only in Ghana but also in Gambia. And he is the founder of Clean Air One Atmosphere. And through OpenAQ, he attended the workshop in Accra in 2018, long before my time in OpenAQ, and was able to meet, a lot of air quality researchers and air quality folks through the OpenAQ network. And so really the power of the community that we have in OpenAQ is something that's also, to be celebrated. So I also wanted to put up here our community ambassador program. So currently we have 10 ambassadors from low and middle income countries all over the world. So they are not air quality researchers. They don't have an air quality background, but they are very passionate about air quality and air quality advocacy, air quality issues. So in their day jobs, some of them are totally not their day jobs are not related to air quality, or some of them are working in environmental law. One is a dentist, one works in public health, one is an IoT professional. And so all of this backgrounds, they aim to use both their backgrounds as well as their air quality advocacy and all of the training that we give in the ambassador program to in this 10-month ambassador program. So yeah, the application for the next cohort for 2024 will be open early next year. So if you know, or if you work with anyone who fits the eligibility that I just mentioned, please do point them to the application for the community ambassador program. We'd love to have a talented cohort through that uses data in OpenAQ to move forward air quality advocacy in their own communities. So moving on to the data in OpenAQ. So for the longest time, we kind of sit at this part of the pyramid of the data science hierarchy of needs for data engineering and management, serving as aggregators of air quality data. So now we're building tools as well to kind of also contribute to the data analysis and characterization. So by building the OpenAQ Explorer, which I'll give a quick walkthrough, we hope to, be able to contribute to the data visualization and hopefully, be able to help in transforming data to information and action. The OpenAQ Explorer, I've been mentioning this is one of our data products, and you're able to access data through the Explorer. It's a graphical user interface where you have your map, you can select the location, and you can also select the pollutant that you want to see. You're able to say, I just want to see reference monitors, or I just want to see air sensor locations. And then just shown here on the sidebar is a quick, summary of what a certain location has. And then you're also able to see many different data providers. Currently, there's 165 listed in here. It's growing. And so you can also see each point. So let me go back here. So if you click any one of these, purple points, it will bring you to the detail page. And so if you click on show details, it'll bring up this detail page where you're able to download the data. And you're also able to see plots. Uh, I wanted to do a little bit walkthrough of that detail page. I know it's a little small on this side, so we're going to zoom in a little bit on those. So like I mentioned, you can download the data here. You're also able to see information about that site and what are the coordinates and whatnot. Then if you scroll down, you'll be able to see the time series and show that in a linear or logarithmic scale, see the last 24 hours or the last 30 days. So just a nice quick look of the data for that specific location. And then you're also able to see patterns. So if you are more interested in the diurnals or like day of week trends, you're also able to see that in the detail page. So hopefully that, gives an idea of the data for that location. So at the bottom of the page here, at the bottom of the detail page, you're able to see, or you're able to download the data from the Explorer tool. So the Explorer, as it is named, is meant to be a way to explore the data that is available in OpenAQ. So you can only download about 1,000 records from the Explorer page. And if you wanted to download more than 1,000 records, you can use either the API or the other data products that we have, like the archive. And so that also this page includes an intro, quote unquote, to the API. So this link here, this API link changes every time you change this date range. So that serves as sort of your introduction to the API as well. So another data product that we have, and actually the main data product we have is the API. So here's the link api.openaq.org, where you're able to interactively build a URL to access the data. And so I'm not going to go through much of the API today, but if you're interested, we're happy to also give trainings and further training on the API usage. But yeah, in general, if you wanted either real time access to the data, say for example you're using it for building an app or whatnot, I think the API would be the access point for you. And then we also have recipes for the API and also some tutorials in languages that are usually spoken. So for example, Python, which is, we also have our newest Python wrapper. And I know a lot of folks write Python, so I do invite you to take a look at our new Python wrapper, and please let us know your feedback and how we can improve this wrapper. And then also there's recipes in the documentation. So yeah, please feel free to check that out. Another new client that we have is the command line interface. So this is for those who are not super comfortable with other programming languages, but want to take a stab into sort of a programming language. So this is available through our GitHub and with the link shown in here. So with that, I'd like to invite you all to, one, use the data in OpenAQ, and two, also, if you are thinking of starting up a project or already starting up a project, putting up monitors or sensors and deploying them in locations, we're happy to help in terms of data hosting and putting it up in a publicly accessible platform, so you don't have to wrangle having a public platform, and you can just you know tell people to have go to OpenAQ and download your data in OpenAQ. Of course, there will always be attribution to the direct source of the data. So say, for example, your research group owns 30 air sensors, and you choose to put that data on OpenAQ. So we're going to put that in there as well. So we can chat more about this. Here are the information on OpenAQ and how you can get in touch with us. But yeah, I think I'll stop here, and I'm happy to take any questions.
Thanks, Colleen, for a really interesting talk. So while we're waiting for questions for other people, I'll ask one. So there was a campaign, a very intensive aircraft campaign in New York last summer. AECOM is thinking about doing a campaign in Atlanta in a couple of years. What role do you see for OpenAQ with these, very intensive short-term measurement campaigns and your long-term data? Like, can you facilitate working with local stakeholders, or do you see OpenAQ more as a support role of just providing historical data?
Yeah, thanks, Kyle, for that question. So I think for OpenAQ, so we can provide like support in a sense that, so since the data in OpenAQ is really more ground level data, so I think it's a good complement for aircraft data. And especially if you're going to also do modeling afterwards, looking at all of these, and you're probably going to assimilate all of these data. And so I think in that sense, since our primary role is data aggregator for ground level data and providing this data in one format, it's going to be more a supporting role for, aircraft campaigns like that.
Thanks. So there's a question about the archive product. Where is that available?
Yeah, thank you so much for that question. So the archive is in AWS. I didn't talk much about it, but it's one of the products where you're able to access historical data and more than 10,000 records at a time, I believe. I might be wrong, but do check out the documentation. So it's available at the documentation is at docs.openaq.org, and you'll see there the details about the AWS S3 bucket, which is how you can access the archive.
Are there any other questions from the folks online? All right, well, thanks, Colleen, for an awesome talk. And if anyone in the audience wants to contact Colleen, either directly to talk to her or let me know and I can put you in touch with her. All right, thank you very much for attending, and I'll see you guys next time.
Thanks, everyone.